a couple of problems on the method that's called extremal principle. So the extremal principle is a technique or principle to prove some problems where you use some extreme points or extreme properties, extreme conditions in the setting of the problem. So the first problem is we are given a set of points and each point is a midpoint of 2 points in the same set. Show that the set omega is an infinite set. Imagine a set of points and every point is a midpoint of another 2 points. For example, if you take this point, this should be a midpoint of these 2 points. And then if you take this point, it should be a midpoint of, say, these two, right? And then, for example, this one, it's a midpoint of this point and then here. So every point has to be a midpoint of other 2 points. So imagine the set of points. So at first, it seems obvious if you try to draw a set where you have every point is a midpoint of 2 other points and it's a finite number of points in the set. But it's so at first we know that it's an infinite set, so we have the statement. How do we prove it? To make a rigorous proof, make it understandable, you can choose, for example, so like the idea of the extremal principle is choosing one of the rightmost or leftmost, so the top or bottom element. So you can choose an element, so for example this one, and then imagine that there are no points past this point, so we don't have no points here. So this is the rightmost element of the set. So if you assume, so with the assumption, assume that this is the omega is a finite set. So when you have finite set, you will have some finite number of points, and then we are choosing the rightmost element. And this point M has to be a midpoint of some 2 points. We cannot have 2 points like this because one of them is on the right of this line and we don't have any points here. So in order to make this M is a midpoint of 2 points, there has to be some points here and here all along this line. So let's say we have A here, B here, right? We don't have any points on the right. Now M is a midpoint of A and B, so there are several points along this line, along this vertical line. Now since we have finite number of points, let's choose the lowest point in this line. So let's say this is the T. So for this point T, there are no points below past this point here, past this T, because it's the lowest, and then nothing on this side. And but T has to be a midpoint of something, so it's impossible to make the T is a midpoint of something, because if you put a point somewhere here on this line, the other side has to be here. If you put something here, the other side should be here. But we don't have any points on the right and below this line. So T is not a midpoint of any 2 points if you make it finite. So if you assume that omega is a finite set, you'll have this contradiction. So it means omega is infinite set. So another proof is probably there are different ways of proving this one, I guess. So another way is to assume the following. So look at assume that the omega is a finite set, and assume that we have the following. Let's say we have 2 points, and then the distance between these 2 points is maximum. The maximal distance between 2 points, the largest distance. Let's say, for example, in this case, this is this is A, and this is B. So in this figure, the AB is the longest distance, and no any distance is longer than AB. But since by the assumption of the problem, B is a midpoint of some 2 points, right? Let's say C and D. It's a midpoint of C and D. And let's draw this triangle ACD. Since B is a midpoint, this one becomes the median. Now, if you look at at this picture, AB, the length of AB, which is the longest distance, it has to be either shorter than AC or AD. So it has to be shorter than one of these two line segments, because AB is located in between them, and it has to be shorter than one of these two, which contradicts to the assumption that AB is maximal. So can we choose the maximal AB distance? Yes, if we assume that omega is a finite set, we can choose the maximal. And if we choose the maximal, we can always find a segment that's longer than the maximal. So that makes a contradiction. So going back to the chain of assumptions, we reach to this assumption, and it turns out we cannot assume that omega is a finite set, which means omega is infinite set of points. Next example is with convex pentagons. We can choose 3 diagonals from which a triangle can be constructed. So when you can construct a triangle using 3 line segments, we need to have triangle inequality, right? Let's say you have this 3, the lengths are A, B, C. The triangle inequality so it has to be A plus B has to be longer than C. Sum of 2 should be longer than the last one, but and for all of them, B plus C has to be greater than A, and then A plus C greater than B. But if you prove that, say, C is the longest one, if you prove the first one, the other two are obvious, because C is greater than A, C is greater than B. These two are obvious. So there are 3 triangle inequalities, but the most important one is to prove that the sum of 2 shorter segments is greater than this longest segment. Now let's draw a pentagon with A, B, C, D, E, and then we can take the longest, let's say this one is longest diagonal. So maximum diagonal, let's say, is AC. So which means if we take the maximum diagonal and then prove that there are 2 more diagonals, sum of which is greater than AC, so 2 diagonals, sum of which is greater than AC, then we can use these 3, because each of them, this one and this one, will be less than AC, because the AC is the maximum. And then we can use these 3 segments to build a triangle. Okay, now let's look at the quadrilateral ACDE, this one, and then let's draw its diagonals. There is a very simple property of diagonals of quadrilateral. You can prove this by yourself. I'll skip that. AD, sum of diagonals, AD plus CE is greater than the sum of sides AC plus DE. So the sum of these two yellow diagonals is DE plus AC. This is easy. So you can prove this, and then this expression is obviously greater than AC. So now we can see that AD plus CE is greater than AC. So we have two diagonals here, here, and their sum is greater than AC. And since AC is the longest diagonal, AC is greater than this one. AC is greater than this one. So which means we can make a triangle using these three diagonals of the initial pentagon. And the final problem, each lattice point of the plane is labeled by positive integer. Each of these numbers is an arithmetic mean of 4 neighbors. Show that all the labels are equal. So if you imagine the following lattice points, here again you can choose the maximum, or so there are, so like every point is every lattice point is labeled by a positive integer. Since positive integers start from 1, 2, 3, 4, you can always choose the smallest label. It could be 1, or if 1 is missing in the entire board, it could be 2. So let's choose the smallest. Let's say M is the smallest label, and here this is M, and M will be the arithmetic mean of its neighbors. So it will be arithmetic mean of this one, this, and these 4 numbers. Let's say A, B, C, D, right? So it's arithmetic mean of A plus B plus D over 4, mean of 4 numbers. M is the following. So at the same time, M is the smallest of all numbers. It means that M is less or equal to A, M is less or equal to B, M is less or equal to C, M is less or equal to D. Now, if you compare this equation and then these inequalities, we can come to conclusion that A is equal to B is equal to C is equal to D is M. They are all equal numbers, because even if only one of them is, even if one of them is greater, let's say A is strictly greater than M, then when you sum these inequalities, you will get 4M is strictly less than A plus B plus C plus D, because of this contribution. A is strictly greater than M. Then it means because of A, the sum will be strictly greater than 4M. If you divide both sides by 4, you get their arithmetic mean is strictly greater than M, which is contradiction by the statement of the problem. The arithmetic mean of these 4 is M. It means all these 4 numbers and M, they are equal. So these 5 numbers are equal to each other, and then you can do the same logic to this point, and then you get these points are equal, and so on. If you do for all numbers, you get that entire plane is labeled by the same number.